I'm ready.
Okay, so welcome ladies and gentlemen. My name is Zofia Makowska, I represent Team Poland, and I'm glad to show you our solution to problem number 11, spring hysteresis. And the problem content states, connect two identical linear springs symmetrically to the mass in a V shape, and apply an adjustable force to the mass. When this force is varied, the resulting motion of the mass depends on the history of changes in this system and applied under certain conditions. Investigate this phenomenon. Well, let's consider the mass on the two springs being located on the opposite side of the force which we now can apply and increase. We can say that it moves towards the force, but after a certain critical point, it jumps to the other side. And the further increase of the force or the decrease of the force and any modification will just cause it to move around the other points of stability. And so the motion isn't completely repeatable. And why is that? What happens there? Well, if we apply a certain force, the springs will react with a spring reaction force, which is equal in magnitude to the ones we apply. But after the force is too high for the springs to react with the force that is sufficient to keep the mass stable, the mass will gain acceleration and jump to the other side. And we are actually able to derive with what force the setup is responding with, depending on the displacement of the mass. But to make it easier for us to analyze, we introduce some dimensionalization of the variables, meaning that we rescale them by the natural length in the system. And here we can see that the motion of the mass depends only on the lambda parameter. And this lambda parameter tells us how much the strings are stretched or compressed. So for the strings that are stretched or neutral, so the lambda, we are able to see that the force in which the force is equal to 0, there's only one such a point. But if we compress the spring, so we get the characteristic V shape we're talking about in the problem, we're able to see that the force is equal to 0 in 3 different points. And to actually be able to compare measurements to theory, we first have to measure the spring constant. We built a setup with consistence of the springs, which we made the spring constant for, and used plastic parts which are 3D printed, and attached them to bearings to assure seamless motion of the mass. And on our stand, we drilled some holes so that we are able to adjust the distance of the lambda parameter. We use the stand with a millimeter paper and a tensometer to obtain measurements of how the force depends on the displacement. Here we can see that it matches both for the stretched system and for the compressed springs, which is amazing, but this isn't really what the problem asks us to do, because we are not to see how the force changes with the displacement, but how the displacement changes with the force. And so we would have to mathematically analyze an inverse function. And we can see that it's quite simple for the stretch setup, as it just follows the S-shaped curve. But something different happens as we compress the springs, because this is no longer a function. It has more than one value for a certain force. Then what happens if we apply force? Well, we do not follow the S shape, we just jump to the other side. And the modifications of the force we are able to do in the setup will just cause it to move along the other part of the curve. And why is that? Why has the middle part of the curve become unstable? Well, this is due to energies in the system. And so for the compressed and neutral springs, stretch and neutral springs, we are able to see that there's only one equilibrium point, which is stable. But for the compressed springs, there are two stable equilibrium points and one which is unstable. And this means that if we build sufficient force in the setup, we will be able to jump from one side to the other, And since we are using a dimensionless parameter, we're able to see how the setup looks, the energy in the setup looks for different ratios of lambda. And for the stretch, we know how it looks. There's only one equilibrium point, 3 equilibrium points, and the bifurcation happens at lambda equal to 1. So this is where the setup becomes interesting. And as we saw, it's not the S shape that we want to analyze, but a hysteresis loop. And this loop changes its area, for example, with lambda getting closer to 1. And to be able to verify it experimentally, we use the setup we already know, but this time we connected it with a thread to a source of force. And we were able to measure that force using a tensometer, which was set at 45 degrees, so that we knew exactly with what force we are acting on the system. And we were able to get that read from Arduino to RPC to get real-time values of how the force changes in time, so what is the back and in time. And if we compare that to a time-step video, which was then tracked, we're able to see how the displacement changes in time. And after comparing those two values in time, we were able to get how the force influences the displacement. Here we can see that, again, we are no longer able to observe the mass following the unstable part of the curve. And actually derived, and this means the height of the hysteresis loop, the width of the hysteresis loop, in particular, the critical force and the displacement for which the mass jumps to the other side. And turns out it only depends on the lambda parameter in the system, which has to be, of course, smaller than 1 for it to be real. And we are able to see that our dimensionalization, so the lambda parameter, is actually applicable for multiple types of springs, and it matches our theoretical predictions. But during our quasi-static analysis, we noticed something very, very interesting, which is the oscillation after the jump. So we can actually approach the dynamic part of the problem, which is visible both on the tracked points and on the Arduino reads. And for those oscillations, we are able to derive the equation of motion, which, if we propose some time scaling, we are able to derive a better one, which is a dimensionless one. And if we solve it numerically for initial values of the displacement and initial velocity, we're able to get the trajectory which we are able to compare with the measurements. And so, since we have both the quasi-static and dynamic approach, we understand the phenomenon in one dimension. But what happens if we start pulling it with a different angle, with a certain angle? Well, we are no longer restraining ourselves to one-dimensional motion, and we are able to derive the forces which act in the system. And those forces, we can see that they are actually connected. The x and y forces are connected. And this means that it won't be so easy for us to get how the functions depend, for example, on the displacement and get a reverse function. And this means we will have to take a different approach. And this means analyzing the energy. The energy in the system comes from potential energy, so from the forces that the springs act with, but there's also a linear potential, which comes from the force we are acting with. And the force has a magnitude and an angle. And if we combine those two and apply the fact that the setup always tends to minimalize its energy, we're able to get the point where the mass should be located for certain parameters. Okay, so now if we focus on how the force changes the behavior of the system, we can set a constant angle and then start pulling with different forces. So if we start pulling it, we will be able, for the stretch space, we will be able to observe a certain trajectory which extends in 2 dimensions. And same goes for the compressed springs. This time we will be able to observe a jump in the theoretical and experimental setup, in our theoretical predictions. And we can see that this jump occurs both in the x-axis and y-axis. And to be able to analyze that motion for the 2-dimensional setup, for the trajectories, we can plot them for both stretch and compressed springs and verify them experimentally using our setup, which consisted of the same setup we used, but this time we had to account for one more thing, which was the fact that after the jump, the angle would change. And so to do so, we ensured a very large distance between the experimental setup, the strings jumping, and the connected to the strings Arduino readings. And this meant that after the jump, we would get a very good approximation of the same angle. And for that, we performed measurements of how for the trajectories which we analyzed before, for different angles at which we pulled. But also, the hysteresis occurred in both x-axis and y-axis. We're able to see that in the x-axis, it's no longer a hysteresis loop shape, but it is quite an interesting one, as it also gets modified by the angle we pull at. And this means that we were able to actually observe the phenomenon in different dimensions. And as we saw, the parameter that determined the behavior of the setup was the lambda parameter, which told us how much the strings are stretched or compressed. And the behavior of the setup was fundamentally due to energy distribution in the setup. So we have 2 stable equilibrium points for that, the lambda smaller than 1, and one which was unstable. And the passing through unstable equilibrium caused cause the system to obtain the hysteresis. And for that, we were able to actually check how the hysteresis look like for different values of critical forces, for different parameters of lambda when the jump happens. And in the two-dimensional system, we knew that the critical force that is required for the force to jump would actually increase. So if we plot the critical values of the force for different phi parameter, so the critical force, we know that it starts as we predicted from a certain one, but then it rapidly increases to infinity. So that as we pull the strings at pi, which is at half of pi, so at 90 degrees, we'll be able to see its approach to infinity. Okay, and so also we were able to analyze the dynamics, which in the system, which are the oscillations, which we know that there are damped oscillations, and thanks to our accurate setup, which not only minimalized the friction, but also we were able to verify the theory by comparing how the displacement